Welcome back. So let's get stuck into the physics. So why are we studying vibrations and waves? Well, in the words of Bishop, our hearts beat, our lungs oscillate, we shiver when we're cold, we sometimes snore, we can hear and speak because our eardrums and larynges vibrate. The light waves which permit us to see entail vibration, and we move by oscillating our legs. We can't even say vibration properly without the tip of our tongues oscillating. Even the atoms of which we constitute vibrate. So vibrations and waves are everywhere in the natural world, and if we're trying to understand that natural world, we're obviously going to need to understand vibrations and waves. So let's just talk a little bit about some of the words that we've just seen. So we've seen a lot around oscillation and vibration, and oscillation is the repetitive variation, typically in time, of some measure about a central value. Often the central value is called the equilibrium point. So it's a fairly abstract concept of any system in which you have something that moves from one side to the other and back to the center, or moves from one state or possibly from one state to another, but has a repetitive motion. What's a vibration? Well, it's a periodic back and forth motion of particles of an elastic body. So a vibration we tend to use when we're talking about some specific thing, some physical object that is vibrating, whereas oscillation is a more abstract general term, but they roughly mean the same thing. So what makes a vibration more than just a movement? Well, there are two key features. There's a periodicity. So what we're saying is if something vibrates, the displacement which occurs repeats itself over and over and over. It's something that is very repetitive. The other thing that we notice is that there's a frequency associated to the displacement repeating itself. So it's not that it just does the displacement and then pauses for a while and then does it again and then waits for an even longer while and then does it again. Instead, there's a repetitiveness to how it displaces. So there's a frequency associated with how many times the displacement occurs in, say, a minute. Sometimes you get systems where there's also a bit of time dependence on that frequency, but we're not going to look at those. We're going to look at systems which have a regular oscillation that occurs in their motion. Okay, so as we've said, everything can vibrate. Virtually any physical system that you come across has the potential for vibration. So you know that if you toss a stone into a calm pond, then you'll get ripples, so the water is vibrating. You might have seen a bridge vibrate when people walk over it or the wind blows. When there's an earthquake, our planet vibrates. So if you have a look, you'll hear about the epicenter of an earthquake, and then there are aftershocks that move outwards in concentric rings, so our planet vibrates. And of course, plants and animals in a variety of ways, right from our atoms up. So pretty much everything can vibrate. In terms of everyday stuff, if you swing on a swing, or you sing, or you play a musical instrument, then vibrations and waves are playing a role there. If you're hearing or talking, then we've got vibrations going into your ears and coming out of your mouth. And in fact, our day-night and our lunar cycle, and in fact our annual cycle, are also all periodic motions that can be described using the stuff that we'll develop. Okay, so I just said everything can vibrate, and you might be thinking, well, okay, we've just been doing basic mechanics. How could something like a ball rolling down a ramp be considered an oscillating system? Well, we can make a little change. So here we've first got a ball rolling down the ramp. Doesn't really look like it's an oscillating system, but if you add another ramp on the other side, suddenly we've turned this into an oscillating system. So there we've got, notice what our ball is doing. It has a periodic motion, so it's repeating the same motion again and again and again around an equilibrium point. So it continues to move, well, now the animation has stopped, but the ball wouldn't. Its motion centered around that bottommost point. So that's an oscillation, that's a vibration. But when it comes to physics, there is kind of a ubiquitous example that gets used, and it's what we'll be using to study vibrations and waves, and that's the idea of a mass on a spring. So you either have a vertical spring with a mass on the end, and you imagine what happens if you kind of go doing and let the mass start springing, or if you've got a horizontal system where you've got a mass that's sliding along a frictionless surface. So again, if we have a look at the motion in both of these cases, you've got, in the vertical case, if you follow the motion of that mass, you'll see that it is moving between a maximum and a minimum point, always heading around an equilibrium point. And the same thing is happening in our horizontal system as well. And it turns out this is a very handy system to try and understand the mathematics and the physics of what's going on when you've got a vibrating system. So let's see if we can use the physics of our mass spring system to try and understand a little bit about what's happening. So if you think about a spring and the way it behaves, and we're thinking about our mass spring system, if we're in situation A, where we've compressed the spring, so it's kind of nice and tightly compressed, what's going to happen to the mass? Well, the spring wants to expand. So in terms of our mass, it's going to exert a force towards the equilibrium point. It's going to try and push the mass so that the spring can expand. So we've got some positive force, a force in the x direction, positive x direction. On the other hand, if we're in situation B, where our spring is just sitting, it isn't stretched or compressed at all, it's just sitting there, nothing's going to happen. Our force is equal to 0. And if we started off like that, then our spring our mass wouldn't move at all. We'd have to pull it or push it a little bit to get it moving. Finally, if we think about what's happening in situation C, here now we've pulled our mass, our spring out so that it's quite stretched. And if you think about holding a stretched spring, it wants to spring back together. So in terms of what happens to our mass, it's going to have a force that's pulling it again towards the equilibrium. So we've got a situation where the force is changing in magnitude and direction. So let's try and explore that a little bit more. Well, let's think about the size of our force. So we want to think about how big it is. We know that when we're at equilibrium, so when we're in this position over here, we know that our force is equal to 0. What can we say if we've got our spring compressed? Well, if you've ever played with a spring, you'll know that when you compress it, the more you compress it, the more it wants to expand. So it seems like our force over here is going to be proportional to the distance that we are from our equilibrium position, which is just another way of saying we're far away from the equilibrium position means that we've really compressed our spring a lot, so the force is going to be big. And thinking about the other situation where we're stretching a spring, again, you'll know if you stretch a spring further and further, it will try and pull itself together more and more. So we come up with the idea that, again, if our displacement from our equilibrium position is measured as x, again, we want to have our force roughly proportional to that displacement. Now, I'm saying approximately. There are some issues to think about. For example, if you crush your poor little spring until it breaks, then it's not going to be exerting a force anymore. It's just going to be a sad dead spring. And likewise, if you stretch it until it breaks, so you go beyond a certain displacement, then it's also not going to be working anymore. So approximately proportional. So you might be thinking, well, this is lovely, but nobody sits around using masses on springs. It's not very helpful. But in fact, it turns out that a lot of real systems, everyday systems that we use, have restoring forces which are approximately proportional to the displacement from the equilibrium. And in fact, if you make sure that the displacement is small, you can model many, many systems with this property. So although we're using a fairly kind of crazy, unuseful mass spring system to model this, the mathematics behind this can be applied to many, many actual everyday real systems. Okay, so let's take this mathematics a little bit further. What are we doing here? Okay, well, we're in a physics course and we're in a classical mechanics kind of frame of mind, so let's look at the forces. What have we got happening here? Well, if we look at our first situation, what are the forces acting on the little mass? Well, we know that we've always got gravity acting, and it's sitting on a surface, a frictionless surface. So we have normal force that's acting upwards, and then we've already said we've got to have the force due to our spring, which is going to push it back towards equilibrium. Now, if there was friction, then we'd have a frictional force that was opposing the motion, but we're in a happy world where there's no friction, so the only force that we have acting in the x direction is the spring force. Okay, so that's our first situation. Now if we have a look at our equilibrium situation, what's happening here? Good old gravity is doing its usual thing, which means we have a normal force, but we don't have a force acting in the x direction because the spring is just sitting there peacefully, it's not doing anything. And in our final situation, again, we've got gravity and we've got our normal force that balances that. And we know that the spring is pulling our mass back towards the equilibrium point. So we have our spring force acting like that. Okay, so this is the last time we're going to talk about gravity and normal forces because we're really only interested in the motion in the x direction. Our block isn't moving up and down, so we're just looking in the x direction. So what we really need to do is figure out a little bit more about this spring force. Okay, we know that sometimes it's zero, sometimes it's not, changes directions. Can we find a way of describing it mathematically? Yes, of course we can. And here it is. Now, you might look at this and go, that's not what I learned at school. And we're going to get to what you learned at school in a moment, but this is the kind of the full thing. So for a mass on a spring, we can write the force that is exerted by the spring as some polynomial times by a minus sign. And if you look at the terms in the polynomial, we've got some constant times the displacement, plus some constant times the square of the displacement, plus some constant times the cube of the displacement, and so on and on and on. And just for the moment, we're saying that our displacement is the distance from equilibrium, and we're assuming that our equilibrium is at x is equal to 0. You can modify this if your x is not equal to 0, but for the moment, let's keep it like this. Okay, does this form for the force make sense? Well, let's think about it. So we're wanting to think about, does this force expression give us the correct looking sorts of forces in the three situations that we've seen so far? Well, let's tackle them one by one. So if we look at situation A, if we think about the displacement that we've got here, remember we're saying that our initial displacement is 0. So the displacement when we've condensed our spring is going to be some negative displacement. So our displacement is going to be negative. What's going to happen if we put a negative into our equation up here? Well, we're going to put a negative in over here. Our spring constant is going to be positive. So the contribution of this term is going to be negative. Because it's going to be positive because we've got a positive here and it's going to be getting confused. We've got a negative here, and it's going to be multiplied by a negative. So in our situation A, this term is going to be positive. On the other hand, this term, we're going to square our negative displacement, so that's going to be positive, and this minus sign over here is going to give us a negative, so it's going to be negative, then we'll have positive, and so on and on. So you might look at this and go, well, we can't really say anything. But here's the important thing. We've been talking about small displacements. So for small displacements, we're going to say the magnitude of our displacement tends to be much less than 1 in whatever units we're working in. So our displacements are small, and we know that if you have something less than 1, then the x squared term is going to be a lot smaller than the x term, because you're going to be squaring something like 0.1, that's going to give you 0.01. So the term that's going to dominate if we've got small displacements will be this first term over here. And so we know that and we've said that in our A situation, that term is going to be positive. So the net result is that our spring force in our A situation is going to be positive. So we've got a force acting in the positive direction. Yay, that's what we wanted. Okay, so at least this crazy thing seems to be working. Let's have a look at our B situation. Well, here we've said that x0 is equal to 0, and we've said that our displacement is equal to 0. And if you put in noughts for all your x's, you get 0. So our force is equal to 0. Okay, so it works for that. And then if we look at our last situation over here, now our displacement, our x, is going to be bigger than 0. So in our C situation, our first term is going to be negative, because we're putting a positive x in there, multiplying it by our positive constant, and then minus sign will turn it negative. So again, using the argument that we're using small displacements, we're going to end up with an overall first term that dominates and gives us a force in the negative direction. So this probably all seems way more complicated than it needs to be, and in fact it is. What we're going to do from now on is just say, okay, we're assuming that our displacements are small enough that we can ignore all the higher order terms, so x squareds, x cubed and stuff. We're going to assume that when you square up our displacement, it becomes so small it's negligible, and that we can just really use this first term, our minus k1x. So this holds if you've got small displacements, and of course so long as your k1 isn't equal to 0, which it isn't for us. So finally we get to where you've probably seen this law before. It's called Hooke's law. We've talked about Hooke, most hated man in science. Okay, well, this is his law, and it says that if you take a spring, the force that it exerts is directly proportional to the displacement from the equilibrium position. So it's taken us a little while, but we have got there. Okay, well that's delightful. We haven't really learned anything new. What do we do next? Well, we remember that we do always also have that F is equal to ma. Good old equation. What does it mean for us? Well, if we're thinking about in the x direction, the only force that we've got acting on our spring is the spring force, so this must be true. The force exerted by a spring must be equal to the mass that we're moving times the acceleration of that mass. And I'm just going to write that as d squared x by dt. So we have two equations that we're using to describe the force exerted by the spring. The second one is our Hooke's law. Well, let's equate these two and see what happens. Well, then we get, so that should be a dt squared. So we get that our mass times our acceleration must be equal to minus our spring constant times the displacement. Let's tidy this up a little bit. So I'm going to divide through by the mass, which I can do because we know that the mass is non-zero. And at this point, you're probably going, oh, that's a differential equation. Yes, it is. That's why we made you look at it earlier. So we will be solving this differential equation a little bit. But let's just do one more thing. Now, it's not entirely clear why I would make the substitution that I'm about to, but it will become plain a little further on in the lecture. So I'm going to let omega, so this is the Greek letter omega, I'm going to say, well, actually omega squared is going to be equal to k1 over m. I know it seems weird, but that's what I'm going to do. So this finally gives me this differential equation. d squared x by dt squared is equal to minus omega squared x. And just a reminder here that x is a function of time. So we're not thinking of x as the independent variable here, it's the dependent variable. It depends on time. It's changing with time. Woohoo! Okay, so now we have an equation that links the acceleration in the x direction to the displacement. And as I said, it's a differential equation. We can solve it. There are explicit techniques for solving it, but in fact, we're just going to look at it and see if we can figure out what the answer should be. So as we've said, remember, x is a function of time. So what we're really looking for, we're looking for some function which, when you differentiate it twice, gives you back the original function times by some constant. We also know that we want to have oscillatory behavior. So at this point, you think, what about sine or cosine? And in fact, you could take either of those. We're going to take our sine function, and we're going to propose that the function x equals a sine bt solves our problem. And in order to check that we're right, well, we need to differentiate it and see if it satisfies the equation. So this is exactly like if you find if you're asked to check if a particular x value satisfies an equation, you plug it in. Well, we're going to check if this function satisfies our differential equation. So we need to differentiate it twice. Here we go. Got dx by dt is going to be whoops, too quick there. Derivative of sine is negative cos. Okay, but we actually need the second derivative, so let's take that. We've got d squared x by dt squared, so now I need the derivative of my velocity. So I've got an a, b, derivative of cosine is sine. Derivative of bt is b, so I get a b squared, and the sign doesn't change. Okay, so I'm just going to rewrite this by switching my a and b squared, because you'll see in a moment why that might be helpful. And lo and behold, look what I've got. My original function was a sine bt, and here it is again, a sine bt. So I can rewrite my differential equation. I can rewrite this as minus b squared x. But if you look back over here, our original differential equation that we're trying to solve is d squared x by dt squared minus omega squared times x. So if I just let b equal omega, then what I get is d squared x by dt squared is equal to minus omega squared x, and that is solved by the equation x is equal to a sine omega t. Okay, so as I say, you could learn an explicit technique for this, but sometimes going the easy route of just thinking a little bit is the way to go. And you could check for yourself that you could in fact use cosine, and that would also give you a valid solution. So there's nothing particularly special about sine, it's just that's kind of how it's always been done, but cosine works just as well. And in fact, we'll see more of that a little bit later. So let's have a look at our solution. So we've got our A in our solution, and that gives us our amplitude. Our A is the maximum value that our oscillation can have. And just remembering back, we defined our omega as omega squared equals k over m, or equivalently, omega is equal to the root of k1 over m. Okay, so that's our solution so far. But in fact, we're going to twist it a little bit. And we want to take into account situations where our equilibrium isn't at zero displacement. So we want to be able to start at any point around our oscillation. And so what we do is we add in what's called a phase angle phi 0. So we're just adding that. Notice that we are adding it within the sine function. And you can check, if you differentiate this, that it does satisfy the differential equation. So this is also a valid solution. We just didn't do it initially because it might have just seemed all too complicated, but we could have. So here is our final displacement equation for something that's undergoing a periodic oscillation. And it works a lot. So it's a close approximation to the true motion. And the smaller your displacements are, the closer an approximation it is. So this type of motion, where we've got a restorative force that is directly proportional to this displacement, is called simple harmonic motion. And it is a mathematical model. Although there are a lot of words in that sentence, it's really just saying that the restorative force, so the force due to our spring, directly proportional to means we've got a constant multiplying the displacement from equilibrium. And I'm just putting the minus sign in because that's the convention. So that's really the sentence and the mathematics, they're identical. It's a mathematical model, and it describes a lot of motions, as we've seen, a mass on a spring, but also a simple pendulum. But slightly more practically, it is pretty good for describing molecular vibration, as well as many other systems. So it can be used in the solar system and moving further out. So it's a model that works on a huge variety of scales, which is pretty cool. So we're going to look at this motion a little bit more to make sure that we fully understand it. But I suggest that now you take a break and go through everything we've done so far. And once it's feeling bedded down, come back and we'll look at the characteristics of simple harmonic motion.